All right, so welcome to the plane curves class today. In the last lecture, we talked a little more about projective curves, and the last thing we did was to prove the projective Jacobi criterion. So let me just quickly review that and then have an example for that. So the result was if we have f a projective curve and p a point on f, then we had a criterion to determine whether it's a singular point or not, namely p is singular if and only if all the partial derivatives of f with respect to all three variables are zero at this point. And we had several comments already on that. Basically, for example, that over characteristic 0, actually these equations already imply that the point is on f. And in the proof, we actually saw that two of the equations usually suffice to show the last one. So, but let's have a look at an example, namely the projectivization of a curve that we have already seen a couple of times. It's somehow our standard example, or one of the standard examples, namely x squared z minus y squared z. No, y, let me write this, y minus x squared minus x cubed. So it's the projectivization of y squared minus x cubed, and that was a curve that in the affine picture we had already seen a couple of times, and that looked like this. So that's the affine picture, and then we add a point at infinity to make it projective. So meaning that we just make this homogeneous by a third variable z, and that goes into this polynomial. So if we just apply this criterion to this polynomial, then we have to compute the derivatives. So df by dx at an arbitrary point is just take the standard derivative, which here would be minus 2xz minus 3x squared. We have the derivative with respect to y, which only occurs here, so it's 2yz. And the derivative with respect to the last variable z is y squared minus x squared. So that means if we want singular points, then all of them have to be zero at the same time for singular points. And it's quite easy. I mean, for a curve like that, it's quite easy to figure out what the points are. I mean, it's a nonlinear system of equation, but they are quite simple in that case. Namely, the middle equation tells you that y or z is equal to 0. But if z is equal to 0, then that would tell you x is equal to 0, and then that would tell you y is equal to 0. So that would give you the 0 point, which doesn't exist in projective space. So that's not possible. But if y is 0, then that's okay, because then this tells you that x is 0, and this would tell you, and this doesn't tell you anything more because it's fine, right? So then z can be anything. And that means that the only solution here is solution in projective coordinate is x is equal to 0, y is equal to 0, and z is anything. So I could just put 1 or any other non-zero number. And that is just the point in the affine part. So we're at z equals 1 in the affine part, the origin, and that's exactly this point. Because here the coordinates are x and y. And that's the only singular point, right? I think we made this computation already in the affine case. The difference is here that we are also covering the points at infinity, and there is actually one point at infinity for this curve, and that would also be a smooth point because it doesn't it doesn't satisfy that one. So in particular, this curve has, even the projective curve has only this as a singular point, and the infinite point also a smooth one. This means this is the only singular point. So in particular, the point at infinity is also a smooth one. So that would be an example. It's very similar to the corresponding affine example where we didn't add the point at infinity. Yeah, that was just to finish up the chapter on projective curves. So here, any question up to that point? Correct. So then the next thing we want to do is talk about, do some more serious thing or prove an actual theorem. There's a whole chapter on that, namely on Bézout's theorem, and also some related ones. And the main question here is in how many points two curves intersect. So that's the question here. To compute the number. So what is the number of intersection points? Of two projective curves. And we'll actually do a lot of the things that we put projective here in brackets. So the final statement will be over the projective space. And if you recall, it was one of the reasons why we introduced projective space, that the situation here is nicer. For example, two lines, I mean, they would usually intersect in one point, but not if they are parallel. But if they are parallel, they intersect at infinity. So the answer here will then always be 1. There's no two cases, except for the case that they are the same, and then we have infinitely many points. But for the first part, I mean, and for most of the proof, we'll be concerned with affine curves, so that might also be easier to deal with. So that's the goal. Probably one of the first questions you could ask about curves, about two curves. And it is, of course, very similar to a question of the type if you have one polynomial in one variable, as opposed to two polynomials in two variables, how many zeros we have there. And there you all know, if you have a polynomial of degree d, then it has at most d zeros if you count them with multiplicities, and it has exactly d zeros if it's algebraically closed. So we compare this to, if we have one polynomial in one variable, say of degree d, then we know that we have at most d zeros if counted with multiplicity. So this we'll always do here. We also have an intersection multiplicity for two curves, that's fine. And we have exactly d zeros if K is algebraically closed. And Bézout's theorem says something very similar for two curves of degrees, say, D and E. Namely, the number of intersection points will always be at most the product of the two degrees. And again, we have equality if K is algebraically closed. So in that case, it's a generalization of the one polynomial in one variable statement that you already know to two variables. So how do we do that? We need, in fact, one prerequisite from commutative algebra. So either you know it already, or we just take it on faith here and assume that. Namely, for this, we need the following. Let me just call the fact here from commutative algebra. Namely, the condition that K is algebraically closed. I mean, it means by definition that every polynomial without a zero is constant. Polynomial in one variable. And as we want to generalize here to two variables, we need a corresponding statement for two variables. So recall K is algebraically closed by definition if every polynomial f in one variable over the field without zeros is constant. And we need something similar for two variables. And in fact, there is something which is called Hilbert's Nullstellensatz, and one usually does that in commutative algebra. So here we just want to assume that. So in commutative algebra, one shows the following thing, which is, say, it's called Hilbert's Nullstellensatz. So it's usually also in English called with this German name. Means something like theorem of zeros. And It is, I mean, the direct generalization of that statement to two variables, one might think at the beginning it would be that a polynomial in two variables without zero is constant. That is also true, but it's not the statement. Namely, the statement is stronger. Namely, it also applies to ideals. Namely, in the following sense, every ideal I in the polynomial ring, let's just phrase it in two variables here. That's the case we need, I and kxy, such that its zero locus, which we call v of I, is the empty set, is the unit ideal. Is I equal the unit ideal. So that does imply the other statement, of course, because if you apply this to an ideal that is just generated, so to a principal ideal just generated by one polynomial, in particular, it would say if we have one polynomial whose zero locus is empty, so that has no zeros, then it's in the unit ideal. So it means, then this is the unit ideal, so it must be a constant. So that implies that statement, but of course that's a stronger one, and that's what we will need. And as I said, so one proves that in commutative algebra here, we'll just use that statement. Again, the way towards Bézout's theorem, so to a statement about the number of intersection points, there's like three lemmas on the way that we want to prove, and that are both actually interesting in their own right and will come up later. So not just some weird statements, but actually useful ones. And the first is about what happens when we sum up all the intersection multiplicities over all points. So that's one thing, of course, that we will do here, namely we want to count these. So if I ask what's the number of intersection points, we will again count them with the intersection multiplicity. So we need to sum up all intersection multiplicities for all the intersection points. And the first lemma will tell you something about what the result of this summing is. So we will not yet see it's the product of the degrees, but we will get one expression for that sum. And that's the first lemma. Let me pause like lemma on summing up intersection multiplicities. Multiplicities. So for that, we take two affine curves. So as I said, we will start with the affine situation. So let f and g be affine curves. And in order for the intersection points to be even finite, we assume that they have no common component. Without common component, so in particular, their intersection will be finite. Okay? So we showed that. That's just to recall, not a statement of the lemma. So we then consider the following ring homomorphism. We call that phi, and that goes from the polynomial ring modulo fg to the product of all local rings modulo fg. Now let me call the step, so it's phi, and the product is taken over all intersection points. So P in F intersect G. And the map is just the natural projection map, so that means any F in here, the class of the polynomial, will be mapped to the corresponding class in the local ring modulo Fg. So called maybe the natural ring homomorphism, mapping each polynomial here to the corresponding element in here, considered as an element in the local ring. And we take the product here over all the intersection points. So and then there's two statements about this. So this map is very close to being an isomorphism, actually. Namely, the first statement is it's always projective. And B is if K is algebraically closed, then it's also an isomorphism. Then phi is in fact an isomorphism, hence it's also injective. That is in fact also a statement from commutative algebra, so maybe those who had attended this class realized this already, otherwise I can say something about this afterwards, but let's just prove that statement first and then I have a couple of remarks about that. So in particular, what this means, of course, is in the nice case where we have an isomorphism, that means if we consider the two sides as vector spaces, then they will have the same dimension. And of course, the dimension on the right-hand side is just the sum of the dimensions of all the factors, and these are by definition the intersection multiplicities. So that means the dimension on the right-hand side as a vector space is just the sum of all intersection multiplicities. And the left-hand side is just one dimension of one vector space. And hence this statement somehow sums up these multiplicities. As it is in any case surjective, this means that the dimension on the right-hand side is always less than or equal to the one on the left. And in the algebraically closed case, we have equality. Right? So in particular, taking dimensions, okay, we get the statement that the sum over all intersection multiplicities, P Fg, is less than or equal to the dimension of this other vector space here, so Kxy modular Fg, that we have on the left-hand side with equality if K is algebraically closed. And that means that simplifies our quest somehow to compute this intersection multiplicity, the sum of intersection multiplicities, to just computing this one dimension here. So that's the goal of the first lemma here. The proof of part A is actually a little simpler than in the notes currently, because we did this year something in that direction already on the homework. Namely, let's first of all say, so this is a ring homomorphism, and that means it will be, in order to show that it's surjective, we don't have to find an inverse image for every element, but as we know that the image will be a subring, it's sufficient to consider to show that we have in the image all the unit vectors. Right? So if we have this product space and have the elements like 1, 0, 0, 0 and 0, 1, 0, 0, 0 and so on, so all the unit vectors in there, we must have the whole ring because the image is a subring. So that may be the first remark. So as the image of phi is a subring of the ring on the right-hand side, suffices to find a polynomial f in Kxy that maps to say maps to 1 in one of the components. Say all the points maybe call this P0, the first point, Fg, and 0 in all the others, we call them Pi, and Fg for all I greater than 0, where the Pi are the intersection points. So that means where F intersect G is F is P0, P1 up to P, whatever the number is, Pm. Because so that is somehow, that's one unit vector. So to have that the image on the right is 1 here and 0 in all the others. So if we have that in the image, then by symmetry we can do it for all the others. Then we have the other unit vectors in there as well. And then as we have a ring homomorphism, you can just multiply the things with other polynomials and sum them up to get an arbitrary element on the right. Let me just put in brackets, so then by symmetry also for the other unit vectors. And then we have a subring and get all of them. So that means all we have to do is find a polynomial here on the left-hand side that maps to 1, 0, 0, 0. And that we can do quite explicitly, actually, namely by one of the homework problems, which was on the first set, was question problem 3 on the first homework set. We saw two things that are relevant for that. And for that, let's just name so we named already the points, but give the coordinates also names. So say Pi is xi and yi. So we put this down here. So set Pi, the two coordinates are xi, yi. And then a homework problem 3 on sheet 1. Oh, for 1, 3. We know two things. And the first thing is that there is a number n such that x minus xi to the n and y minus yi to the n is 0 in this local ring on that side here. So we know there is a natural number such that x minus xi to the n and y minus yi to the n is 0 in OPI mod FG. So we had it there for the 0 point, and it just said like x to the n and y to the n is 0 in the local ring at the origin. But that's of course just a shifted one, huh, with the coordinates. So that's the same statement. And we have this in principle only for one I, but then of course we can take, as we have finitely many only, we can just take the maximum of all numbers that we need, and then we have it for every point, right? So there is such a number. That was, I think, part A or something of this exercise, that there is a number that's such that this holds. And for that now we set first a polynomial g that should be the product of all these things for all the xi and yi that are not equal to the coordinate of the point 0, p0. So that means we take the product over all x minus xi to the n times the product y minus yi to the n. And the product is over all I such that xi is not equal to x0. And here the overall I such that yi is not equal to y0. So that means that has the property for any point Pi that is not P0, this will be 0 in the local ring, right? Because, I mean, if I have a different point, then either the x coordinate is different or the y coordinate is different. So that means we will contain one of those two factors in there, and hence it is 0 at this point. So G will be 0 in OPI mod FG for all I greater than 0. But for I equals 0, it's not 0 because it has a non-zero value at the point. If I plug in x equals x0, then we have all the numbers, I mean by construction essentially, which is non-zero. So then G of P0 is non-zero. And that means that 1 over G exists in the local ring at P0 mod FG. And the second thing that we saw on this homework problem is that every element of this thing has a polynomial representative. Again, by homework, same question, same problem. 1 over G has a polynomial representative. So let's call this H. So i.e. 1 over G is H in OP0 mod FG. So these are the two parts that we need. So they're both from the same homework problem. And what we now just take is G times H. Because G is a polynomial, H is a polynomial. And we have a ring homomorphism. So f, so g times h maps to phi of g times phi of h. And this g will mean that for all points not equal to 0, we get 0. And at the point 0, g is the inverse of h, so we get 1. So that function does exactly what we want. Then phi of f times g, so that is a polynomial now, maps to 1 in the P0 component, because there h is 1 over g by construction, and it maps to 0 in all other Pi. And that's the statement from here, up here. Right? Statement here. And that's the first part. So that means that this map is always surjective. So last time I didn't have this homework exercise, so I did part of this in the proof in the notes, but now it's simpler. It looks quite constructive, except for this part that finding a polynomial representative is maybe not. I mean, you would have to know how to do that if you want it explicitly, what we have this statement in the homework. So that does always hold. I mean, we don't need anything about the ground field. Is there any questions about that? Yeah. That is okay, because then, I mean, so these two factors are both 0 in the ring, and at least one will occur here, right? So if I have a point that's not P0, then at least one of the coordinates must differ from the point. What? Oh, you say, right. So we get a, then we do have the factor x minus xi in there. Oh, that's true. That's bad. Right. So I didn't think about that, but no, wait. No, wait. I mean, you never have. No, that's not true, right? I mean, you never have any of those numbers 0, because you only take those xi where xi is not equal to x0. Right? And only the ones yi where you take yi not equal to y0. So I mean, I mean, by definition here, that will, I mean, none of the factors will be 0 at the point P0. So, good. It's okay. Anything else? Great. So that's the surjectivity, and that does not need anything about the ground field. Now, if K is algebraically closed, we'll actually use this Hilbert's Nullstellensatz that we had in the fact before, and we'll apply this to a particular ideal. Namely, we consider the following ideal. Which is usually, if you know this from commutative algebra, it's sometimes called an ideal quotient. I just have to start the other way around. Say we want to show it's injective, so let's take an f in the kernel. Right? So let f be in the kernel of phi, and we have to show it 0. Right? And for that, now consider the ideal. So we have a given f at we want to a polynomial, so f and kx 0, such that phi of f is 0. Or you might want to write phi of f bar is 0, because we start here with the quotient space. But we want an actual polynomial to start with, and we consider the ideal I, which should be all polynomials such that g times f is in the ideal generated by f and g. So that's an ideal in the polynomial ring in 2 variables. Easily check the ideal properties, and it's given not by its generators but rather by properties. So we really need if we want to say something about this ideal, we really need the Nullstellensatz. And the claim is that if we use the Nullstellensatz, it's okay to show that this has empty 0 locus. suffices to show that the zero locus of I is empty, because otherwise, if we had a point in there, all right, otherwise by the Nullstern, that's the point. So if it was, what I'm saying, so what is the Nullstern that says? So if I have an ideal whose zero locus is empty, then the ideal must be the unit ideal. And I want to show what? Wait. I want to use that. So let me show that it is empty. Yeah, exactly. Because you want to show that because not otherwise. A bit confused today, it seems. So we want to show that the ideal has empty zero locus because then by the Nullstellensatz, it will be the unit ideal. I'm going to use it that way. And if it's the unit ideal, that means 1 is in there. And 1 is in there, it means that F is in Fg by definition of I. And that means that F is 0 in this quotient here. Right? So that means injectivity. Well, that's why this is sufficient to show that this has an empty zero locus. And there we actually want to do by contradiction. So assume that there was a point, to prove this, we assume we had a point in there. Then this must actually be one of those points because this ideal here clearly does contain the polynomials f and g. Because if I put f here, then that is true. It's just little f times capital F. So that means we will also have that p is in v of f and it is in v of g. Because f and g are in that ideal. And that means this p must be one of the points that are in the map. So for others, it's impossible right away. It must be pi for some I. But that means now that as we have our element f here, which is in the kernel, that in particular f maps to 0 in this corresponding factor. P is one of those points. And so maybe let's keep the statement on the board and erase this. So P is one of the points. So in the local ring at P, this must be 0. The element F. So as the F bar is in the kernel of phi, this means that F is 0 in OP, so OPI, but it's also OP mod FG. And that means that it's in this local ring a linear combination of F and G. So that means we can write F in the local ring as something times F plus something times G. And the elements here would be quotients of polynomials. So we could write it as something like A over G plus B over G, where A, B, and G are polynomials, and G is non-zero at the point. So A, B, G are polynomials in X, Y, and G at the point P is non-zero. And that's what the elements in the ideal look like. Well, what does that mean? That means that if we multiply with F and GF, this A F plus BG, which is in the ideal FG, and that exactly means that this G is in the ideal I, because that was defined to be all G such that GF is in this ideal. So that means G is in this ideal I. But now this doesn't work because we have a point P that's in the zero locus of the ideal. of P is in V of I, and if G is in there, it means that G of P is equal to 0. And that is a contradiction to that it's not 0. Here we have it's not 0, here we have it is 0. Well, that's a contradiction, so it doesn't work. And hence, that shows here by contradiction that there is no such point in the 0 locus of I, and that it's empty, and hence by the Nullstellensatz we get that F will be in the ideal of capital F and capital T. So that's the first lemma here, which is, and that doesn't need the algebraically closedness. Actually, about this thing, so if you know some commutative algebra, maybe you realize in between that you know this already. Namely, you talk then, it's only for those who are in commutative algebra, then you talk, for example, one thing you talked about, one topic was Artinian rings. An Artinian ring is a Noetherian ring of dimension 0, and that is one, because it's a Noetherian ring because we have this thing here, right? Because that's a Noetherian ring, so there will be a Noetherian ring, and as it's just a finite number of points, it's an Artinian ring. It has dimension 0. And there is a structure theorem about Artinian rings, which tells you that every Artinian ring is the product of all the localizations at all maximal ideals. Now, over an algebraically closed field, all the maximal ideals just correspond to points, or the maximal ideals, the components are just that. These are just the localizations at all the maximal ideals. And so that is just the structure theorem, just in the case you've heard that. And if K is not algebraically closed, the statement about Artinian rings doesn't need K to be algebraically closed, but just the point is that not all maximal ideals are of that form. So if we included all maximal ideals of that ring, then we would still have an isomorphism, but not all of them are points. So here there are some of them missing, right? That's why we need algebraically closed for it to be an isomorphism. Otherwise, you would get an isomorphism if you just take the product with all the other maximal ideals as well that we just left out. And so it's still surjective, but it's not injective. We just write something down about this, but if you haven't heard it, it doesn't matter. But if so, then there's actually nothing to remember here because you know that already. So that's one remark. So part A is so compare. So it's just a commutative algebra remark. As said, which you might ignore if you don't know that, namely kxy modulo fg is an Artinian ring. Namely, it's Noetherian, which you can see as the polynomial ring is Noetherian, and hence the quotient is as well. And it's of dimension 0 because it's just a finite set of points. Dimension of the ring is 0. And hence, by the structure theorem, for Artinian rings, this means kxy mod fg is isomorphic to the product of all its localizations at the maximal ideal. Maximal ideals, and these maximal ideals in the algebraically closed case, if K is equal, K is the algebraically closed. These are just points. These are just the ideals of points. That's part of the Nullstellensatz, or one version of the Nullstellensatz, that the maximal ideals in the polynomial rings are just the x minus xi, y minus yi. And so that means if we put all the maximal ideals in here, we would always have an isomorphism. But for a non-algebraically closed field, we leave the ones out that are not of this form corresponding to points, and hence it's still surjective, but not. So both parts would follow from commutative algebra. Yeah, but that's just a side remark. And maybe also, if you have heard it, it helps you to understand the commutative algebra statement, so what it actually means geometrically. Because what it means geometrically is actually, of course, some kind of interpolation statement, right? So what we have here is, maybe that's easiest to imagine if all those intersection multiplicities are 1. Namely, if all the intersection multiplicities are 1, which is somehow the general case, then all these factors will just be k, and just the map will just be the evaluation at that point. And that means that what we do is we are looking for a polynomial that has prescribed values. So if we take the surjectivity, we prescribe a value at each of the intersection points, and we are looking for a polynomial that takes on all these values. So it is sort of an interpolation statement. It's the corresponding thing. If in one variable you're picking finitely many points on the line and looking for a polynomial that takes on all these values at the points. So it's a very similar thing, just that the points are the intersection points of f and g. So geometrically, if if all the intersection multiplicities are 1, so if we had p of fg 1 for all p in the intersection, we have that this OP mod fg is just isomorphic to k for OP in the intersection. And phi is just the evaluation at all those points. So that part A of the statement, the surjectivity, is just saying that you will find a polynomial that takes on specified values at all those points. So this is 1, we have this k for all p and f and g, and hence, and phi is the evaluation at all those points. And hence, part A of the lemma is an interpolation statement. Namely, one can find a polynomial with given values at all these points. At all points of f intersect g. That is if all the intersection multiplicities are 1, right? Because then this is k. If they are not 1, then it's a more delicate statement, right? Because then this is not just evaluation at a point, but it will somehow remember derivatives as well at this point, and then it's an interpolation statement of that type as well. But that's in general how you could imagine that statement of lemma 1. Right. Is there any question about that? So if not, then we can actually continue a little with this idea that is an interpolation statement. So you will find a polynomial that takes on given values at all these points. But if you want to do this, then, I mean, if you think from interpolations by polynomials on the real line, you also want to sort of have a bound on the degree of the polynomial, right? I mean, that you find just any polynomial that has these values is not so interesting, but you want the degree sort of to be as low as possible. And that is, in fact, a statement in the next lemma that would tell you what degree you would need at most here in this part. That is, so which degrees of f are needed for the interpolation. So that leads to the following lemma, which is the next one that we need. For that, we only look now at the left-hand side. So we don't need the map anymore for the moment, but just consider this ring here, kxy modulo fg, and ask if we have a polynomial in there, what would be a representative of the least possible degree? Right? I mean, in any case, we can write any element in here, well, by any degree. And then the question, how can we reduce that? And that's the lemma that tells something about that. So we start again with f and g. So let f and g be affine curves. And for that, we need a slightly different assumption, not that they have no common component, but that their leading terms have no common component. So let's denote the degrees by m and m. So with m is the degree of f, and n is the degree of g. We assume that the leading terms, and that we called fm and gn, so these are the leading terms, the ones with the highest degree, have no common component. What does that mean geometrically? We had seen that the leading terms of polynomials describe the points in the projective closure. So we had an alpha, if we have an affine curve f, then there was a projective closure by taking the homogenization of this polynomial and then considering the zero locus in projective space. And we saw that if we intersect that with the line at infinity, we exactly get the points, the 0 points of the leading terms. And that means if those leading terms, which are polynomials now in two variables, of course, and consider the projective zero locus in one variable on the projective line, then these will be exactly the intersection points at that line at infinity, and having no common component just means that they have no intersection points at the line at infinity. So, i.e., this means geometrically that the projective closures of f and g, which are given by the projective zero locus of fm and gn, don't meet at infinity. So all their projective line, all the points, intersection points in projective space will actually be in the affine part. That's the geometric version of the same assumption. Well, that's an algebraic lemma, and so the corresponding algebraic assumption is just that the leading terms as homogeneous polynomials in x, y do not have a common component. Then the statement here is that if I take a polynomial in this ideal here, f and g, in any polynomial, we call this little f, then fg can be written maybe we should give it the degree here, or the degree here little d. Any polynomial f of degree d can be written as f is a capital F plus b capital G. So that, of course, is always possible. That's the definition of the ideal. But with the corresponding, with a degree condition, namely the degree of A is at most what you would expect, namely the degree d of f minus degree m of capital F, and correspondingly b, so b is less than or equal in degree d minus n. So that means if you have here something of degree at most d minus m and capital F is of degree m, then this will be at most of degree d, and correspondingly this is of degree at most d, and that means there is no canceling here between those terms. So in principle it might be, of course, that a and capital F have higher degrees than the ones occurring in F, so that this has degree bigger than d and this has degree bigger than d, and they just cancel out in the two. Well, the statement is, of course, that might happen, but the statement is that any element in the ideal can be written in this form where this does not happen. So that's the statement here. Yeah, so let's say something about the proof. And for that, we start with any representation of that form. So we clearly have that we can write F as A capital F plus B capital G for any AB without any degree assumption, right? So that's the definition of the ideal. And what we want to do is now we take such a representation, say with minimal values of the degree A, and show that this is at most this number. So take such a representation with the degree of A minimal, and we want to show that then it's at most d minus m. And so why is that? So we claim that then this degree bound holds. So degree of A is less than or equal to d minus m. So let's assume, so why is that? So assume this is not the case. So assume not, i.e. the degree of A is bigger as d minus m. That means that the degree of AF is bigger than d, and as this has degree d, there must be some cancellation in those two terms. Right? That means that also here the degree of B is bigger than d minus n, and the leading terms just cancel out. So then the degree of A times F is greater than d minus m plus m, which is d, and that is the degree of F on the left-hand side. And so this means there must be a cancellation in the sum which means that the degree of B is also bigger than d minus n, and the leading terms just cancel, at least the leading terms, right? If there's more than that, they have to cancel as well. Relation sum, so hence the degree of B is also bigger than d minus n, and the leading terms in AF and BG cancel. And because the leading term has degree higher than D, and there is no higher than degree term in little f. So let's really have a look at these leading terms alone and denote them somehow. So capital F and G are they're not homogeneous. M and F and G are not homogeneous. So is that one? Let's have a look at the leading terms, what they are. And of course, for F and G, they are Fm and Gn. That's how we call them. And let's introduce a name for the leading terms of A and B. Let's call them A little star and B little star. So if A star and B star are the leading terms of A and B, then we must have that the leading term of AF, which is A star capital FM, plus the leading terms of the second, so B star Gn is equal to 0, right? So that's the equation just in the leading term, which means that A star F is minus B star G. Gn. And now we need that there's no common component in Fm and Gn. So if we consider the prime factors of those polynomials, then the factors of Gn cannot be in Fm and the ones and vice versa. So all the factors of Gn must be in A star and all the factors of F must be in B star. So as Fm and Gn have no common component, we must have that Fm is a multiple of B star and Gn is a multiple of A star, and they still cancel, right? So that means Fm must be of the form C times B star, and Gn must be of the form minus C times A star, right? So that. So there can be more factors which are in both A star. No, I think it's the way around, right? What is it? All the factors of Fm are in B star, but we don't know anything about A star and B star, so they can have common components. So they must be an FC times. And B star can be a C times, and A star has a CGN, and this has CFM, and then we must have a minus, right? So the argument here is that all factors of Fm must be in B star, and all factors of Gn must be in A star. And that's just this one. There can be more factors in A star and B star, but no common in Gn and Fm. So that's where we need the assumption, and then we can just form a new combination. Then our polynomial that we started with F, which was AF plus BG, we can also write it as A, and then we take F minus, what do we want? We want the leading terms to cancel, and the leading terms was the Fm. So what is the thing that we need here? We want to take F minus we want to take this with A, like this here. So A minus, and then get a CG, is it that one? Yeah, times F plus B plus C G F times G. Let me check that one. So that is still true, and because I just subtracted CGF and I added CGF, so it's clearly an equality. And here in this term here, this is A star. So the leading term here is the A star. And so this means in this expression here, the leading term cancels and we get a lower degree in. And so the degree here is less than the degree of A. And well, that either you formulate it as a contradiction, so say this doesn't work because we assume that we had the minimal degree, or you think of it constructively and say, so assume the degree was bigger before, then we just have constructed a new one with the smaller, and we can continue that until we arrive at this bound that the degree is at most d minus m. But here formulated by contradiction, so we say that this is a contradiction to minimality of the degree of A. Right? But that is actually pretty constructive. So that means if we start with any element in the ideal, and first of all you find the representatives where A and B have quite big degree, then you can consecutively reduce the degree until you arrive at this point that the degree of A is at most d minus m, and the one of B is at most b minus n. Right, and that gives you some degree bounds, so to say, in the first statement that we had today. So, is that okay? Any questions? Thing and raise here. So otherwise, as I say, there was like three lemmas before the main theorem, but this third one is already pretty much the theorem of Bézout. This lemma 3. And that tells you something about the dimension of kxy modulo fg, as we had in the first lemma, right? So we had summed up the multiplicity already, and now reduced that to the case where we just have to compute the one dimension of kxy mod fg, and that tells you something about this. So for this, say that f and g be two affine curves. Everything here is affine. With now again without common component. And again, as before, we say m is the degree of f and n is the degree of g. Then again, there's two statements, and the first one is that the dimension of the thing, the polynomial ring kxy mod fg is, as already anticipated, the number that will occur in Bézout is the product of the degrees, m times n. And b, that if we have the assumption of lemma 2, namely that not just f and g have no common component, but also the leading parts have no common component, then we have equality here. M and gn also have no common component. That's a different condition, right? I mean, they're different polynomials, so it might be that the one holds and the other doesn't. So if m and gn also have no common component, then we have equality in A. That's the statement, right? And that is, I mean, that will be the Bézout number. I mean, as I tell you, the number of intersection points counted with multiplicities is the product of the degrees, and that's very close. I mean, if you take part B, that's already very close. Yeah? The only thing is pretty much that what we have to do is that we need that the leading terms have no common component, which just means that they don't intersect at infinity. And so what we'll then do at the end is just we move coordinates so that this doesn't happen. Right? And then we are in that case and we get equality, and that is the sum of the multiplicity. So in that sense, this is pretty much the final result of Bézout. So then Bézout is really just a corollary of that. Yeah, how does that work? That goes in the direction of exact sequences, or at least a sequence of two morphisms. Maybe let's do the following. So we have named already the degrees m and n, and we consider for all degrees bigger than at least equal to m plus n the following maps. So we'll consider them as vector space homomorphisms. Namely, we start with the following. So we start with the polynomial ring xy, but only in certain degrees, and I'll note this as so less than or equal to, and then start here with a d minus m and d minus n. So this here will denote all polynomials of degree at most d minus n, right? That's the vector space. And now we take here and take the product of that with all polynomials of degree less than or equal d minus n. Now this maps by some map, which I want to call alpha, to polynomials in xy of degree less than or equal to d, and then by the natural projection maps to the quotient kxy modulo fg. So the map pi is just the ordinary projection, right? The quotient map. We'll just write here quotient map. And this map here does the following. So it takes two elements, a, b, polynomials. A has degree at most d minus m, b has degree at most d minus n. And then we've just mapped this to af plus bg. Right? And that works because f has degree m. So if we have degree less than or equal d minus m, and here g has degree n, then this sum will have degree at most d. So this actually maps to the thing in the middle. So we could restrict, we could consider the map also for arbitrary degrees, but to count dimensions, it's better to do that with restricted degrees, because otherwise the dimension would be infinite of these spaces, right? So these are all finite dimensional vector space. Now that's a sequence of two maps, and we want to check how far this is from being exact, or meaning like from the first being injective, and like the image here equals the kernel of that, and that being surjective. So it is not an exact sequence, but we can actually compute pretty much all the kernels and the images. That's what we want to do. So let's start with the first map with the kernel. So what can we say about the kernel of alpha without any further assumption? So we are in both cases A and B together at the moment. We're not using that assumption. So what can we say about the kernel of alpha? Well, the kernel of alpha is obviously just those AB such that AF plus BG is 0, the definition. And that is an equation similar to that one. So that means AF is minus BG. And also here we have an argument similar to the one before, because F and G have no common component. And that means that all the irreducible factors of F cannot be in G, and the factors of G cannot be in F. And so this means all the ones of F have to be in B, and all the ones of G have to be in A. And that again means that A is just a multiple of G, and B is the corresponding negative multiple of F. Very same argument as that one. So as F and G have no common component, we can write this as the set of, so the A must contain all the ones of G, so this will be CG, and then here we have the negative B times F. So B must contain all the ones from F, and that with corresponding negative signs, where just C is just anything. And what does it mean, anything? I mean, we have restrictions on the degree. Namely, the C can be something of degree. What do we want? So we want to end up with degree D, and the, what is it? So no, we want A to be, so this must have degree at most D minus M, but G has degree N. So C must have degree at most D minus M minus N. Right? Because then, if that holds, then only then the degree of CG will be at most D minus M, and the degree of CF will be at most D minus N. So that's the thing. And so that means we can, write it in that way. So it's something, let me write it in a suggestive way, saying this is G minus F times the polynomial ring XY in degree D minus M minus N. So that will be the kernel. So it's not injective. It's clearly not injective, but we can write down explicitly what the kernel is. And that needs the assumption that we have no common component. In particular, we could use this to compute its dimension, right? Because that means as a vector space, this kernel is isomorphic to that thing here, and we know how many elements, what the basis is, what the dimensions of that vector space. We'll use that in a minute. So we know something about the kernel. Then for exactness, you would have to compare the image of alpha with the kernel of pi. And I think at least we can see that one sits in the other, right? So the image of alpha sits in the kernel of pi, right? So if we come from here, we have AF plus BG, that clearly is 0 here. So that means clearly we also have that the image of alpha sits in the kernel. And the rest we just leave for a moment and just start computing. So over this we get. I mean, we finally want to use that to compute the dimension of the thing on the right. I mean, that's the statement in the lemma. So we want the dimension of the final space, but let's just start with the dimension of the image of pi, which would be the same if it's surjective. We'll just see this in a minute. But start with the dimension of the image of pi. And see what we get. And that's start with the homomorphism theorem, right? So the image of pi has as a dimension the dimension of the starting space minus the dimension of the kernel. So it's the dimension of axy less than or equal to d minus the dimension of the kernel. And that one could just compute, right? I mean, what's the space of polynomials of degree at most d? And if you compute this, you will see it's just a combinatorial thing, and it's d plus 2 choose d. Minus the rest I just copy. Dimension of the kernel of pi. I mean, that's just some standard combinatorial counting here in this part. Yeah. So is that the right number? It is checked. So or is there a shift by something? I think I just claimed this in the notes. I'm just checking if this is correct. So the d is, if d is 0, then we just have the constant, and here we have 2 choose 0. That's 1. I mean, that's trivially true. Okay, I hope this is true. So for degree 1, it would be 3 choose 1, which is 3, and then we have 1 xy. Yeah, that seems okay. Anyway, that's the number. And now we can use that. So the kernel is more than the image. And so here we have it with a minus. So I can make this a less than or equal to if I replace the kernel by the image. I can write this less than or equal to d plus 2 choose 2, and then minus the dimension of the image of alpha. Right? So that's this statement here. Somehow, always maybe one. Now use the homomorphism theorem again. The dimension of the image of alpha is the dimension of that starting space minus the dimension of the kernel of alpha. So that is the same as the first thing we copy, d plus 2 choose 2, and then minus dimension of the starting space. So that is the dimension of that plus the dimension of that, and that's a similar number than that one. It just with the degrees replaced by d minus m and d minus n. So we would here get d minus m plus 2 choose 2, and then minus d minus n plus 2 choose 2. That's the dimension of the starting space of alpha, and then with the double minus, so with the plus, we get the dimension of the kernel of alpha. So these two parts here would be the homomorphism theorem. And the kernel we just computed, right? And the dimension is just the same as that dimension, and that's again a dimension of that type, now that the degree is just d minus n minus n. So by that one here, that is the same as d plus 2 choose 2 minus the rest I just copy, d minus m plus 2 choose 2 minus d minus n plus 2 choose 2, and then plus, so with the degree d minus m minus n. Okay, now that's just some stupid computation, right? In d and m and n. So there's none of these maps involved anymore. That's just a number. Obviously, I don't want to write this down explicitly and multiply all this out and cancel stuff. You could just do that for yourself, and you might guess what the result is in the m times n. So the d cancels out entirely, which you could somehow see because, I mean, these are all quadratic terms in d, like it's a d plus 2 times d plus 1 over 2. So there's a d squared over 2, but you have this in all the terms. So the d squared over 2 will cancel, the plus and the minus and the minus and the plus, and the linear will cancel as well. That's pretty much the statement that we have a d, I mean, that the sum of those is the same as the sum of those. So we can just compute that. The result that we get here at the m is m times n. In particular, that holds for all d. Right? That may be surprising that the d cancels out. And what that means is that we can actually fill in the one gap about whether pi is surjective or not. Because pi is clearly surjective if we don't restrict the degree. Right? I mean, kxy to kxy mod fg is surjective, but here we restricted the degree. However, we see that the dimension of the image does not get bigger. We get the same estimate here for all d. And that means that we get the same estimate also if we don't restrict the degree. Whereas this is independent of d, we get that also the dimension of the, that this holds also if we don't restrict, we get the same same estimate. If we don't restrict to a certain degree. And in which case, of course, pi is surjective. And that means that the dimension then becomes the dimension on the right-hand side. And so that means the dimension of kxy modulo fg is less than or equal to that number, m times n. And that was part A, right, of the statement. Okay. And well, the second one is then easy because that is just lemma 2, right? So the statement here is now that we have equality. So to show that we have equality just means there was only one line in which we have a less than or equal to. So the question is whether this is equality or not. And there we used that the image of alpha is in the kernel of pi. So if we knew that this was an equality, that the kernel of pi is also in the image of alpha, then we would have equality all the way down. And we would have equality here as well. And that is just lemma 2, right? Because lemma 2 said if we have something in the kernel of pi, namely a polynomial of degree at most d, that maps to 0, that means that is in the ideal fg, then we can write it as af plus bg, where the degree of a is at most this and the degree of b is at most that. So the other inclusion here holds under this assumption that we had in lemma 2 just by the statement. And then we have equality here, we have equality here, and hence also in the end. So moreover, if Fm and Gn have no common component, and by lemma 2, we also have that the kernel of pi sits in the image of alpha, that is just with this pi and alpha, just the same statement just rephrased. Right? So kernel means it's something in the ideal Fg and when of degree at most d, and we write it in that form. And hence we get equality in the thing here. Because that's the only point where we needed it. And that's the only part where we have less than or equal to. And so this means we also have equality in the final result. So in that one here, which is n. And that is the part B that we wanted to show, and that ends this. Right. So that is lemma 3, and as I said, this is pretty much Bezout already. Right? Because if we have, let me just say this again, but I'll just write this down in a minute. If we have two projective curves that don't meet at infinity, which we can assume by a coordinate transformation, then I mean, of course, we have to assume in any case that f and g have no common components, otherwise we would have an infinite number of intersection points. And this assumption just means that they don't meet up at infinity. And then we get the statement it's less than or equal to the product of the degrees, and equal if we're algebraically closed. Just write this down. What are the questions about this proof? On the board then. So let's put this together then. So all together, we get as the corollary Bezout's theorem. Which says for that we need now projective curves at f and g the projective curves without common component. And we clearly need that because otherwise the intersection points, number of intersection points would be infinite and we couldn't sum over the thing. All the intersection multiplicities would be infinity. And for our case, I put this here in brackets. Actually, I want to assume over an infinite field. That is not really necessary, but for our proof it is. We'll just see it in the proof, so it holds otherwise as well. But for our proof it is necessary. So that's why I want to put it here. So without common component over an infinite field. And then the statement is, then if we sum up over all intersection points, just a finite sum, then all the intersection multiplicities fg will be less than or equal to the degree of f times the degree of g. And if k is algebraically closed, we have equality. So similar to the statement that the number of zeros of one polynomial is always less than or equal to the degree, and we have equality if the field is algebraically closed. So that is the statement. And for that, as I said, we just have to put things together. And as this is now a statement about projective curves, and all our lemmas were about affine curves. We just wanted to reduce to that case by picking suitable coordinates, or making a linear change of coordinates so that everything happens in the affine case, in the affine part. And that is the one part actually that would not work for finite fields. That's somehow a bit unfortunate. But otherwise we would have to rewrite all the proofs in terms of projective stuff, which is always a bit harder. So I did it that way here. So the proof, let me just quickly do that, as there's nothing really new to be done. So what we want to do is I say that by a coordinate transformation, we can assume that f and g don't meet at infinity. And that is something actually, so let me just put this in brackets here, that actually needs that k is infinite. Because if we had a finite field, then if our whole plane only has finitely many points, it means it might be that the curves meet in every point, and then we couldn't do that. Right? But if we are over an infinite field, then we know that there will always be points where the curves don't pass through. So say this needs that k is infinite. And what we could do, for example, if we have an infinite field, then we clearly, first of all, find a point that's not in the intersection. So first find a point, say Q, which is not in the intersection. So this can already fail for finite fields, right? But for infinite fields it cannot. And then we only take another, there was only finitely many lines through the point that meet any other point, because there's only finitely many points in the intersection, and there are clearly infinitely many lines through the point. So we could then pick a point R not equal to Q, such that the line through Q and R contains no intersection point. Of f intersect g, and that we transform to the line at infinity, right? So then we have no intersection points at infinity. And transform this line to the line at infinity. Right? So that we can do, but that needs an infinite field. And so the reduction from projective to affine unfortunately needs that. But there are other proofs of Bézout that don't need that, so it would hold also for finite fields. Yeah, and then the rest, I think we all did that, right? Because then we have the assumption. So then we write this down as the term that we want to compute, the sum of all intersection multiplicities, is now the same as if we did it for the affine curves over the finite part, because they don't intersect at infinity. So then by what we did here, we can just sum over all points in the affine part, which is given by the inhomogeneous polynomials fi intersect gi, and then p of the inhomogeneous part, fi gi. And then we use our lemma 3. No, first 1. First we sum up the multiplicities. So that means this sum is less than or equal to, by lemma 1, this dimension of kxy modulo fi gi. And here we have equality if k algebraically closed. And this dimension we just computed here. Okay? And there we are always in the case B, because we don't have any common components of the leading term. And hence there we always have equality by lemma 3. So I'm just finished in a minute. So this is equal now by lemma 3, as there are no intersection points at infinity. We're actually in the case B, so lemma 3b. This is the same as m times n, and m times n was the degree of those polynomials. So yeah, first of all, it would be the degree of fi times deg gi, but f and g have no components at infinity, so that means that would be the same as the original degrees, deg f times deg g. And that's the statement here. So that means we always have less than or equal to, and we have equality if k is algebraically closed. Right? So that's just putting things together. And that finishes that thing here. Yeah, so that's a really central theorem, I guess. So we'll next time when we'll use that in many, many cases, and also have a similar theorem next time that uses the lemmas before, not just the theorem, but also the previous work. But that will just pull its way throughout the class, I guess, for the remaining weeks of the class. It's the very first thing you could ask, and it's very important. Yeah, so are there any questions? Otherwise, we just stop and then continue there next week at this unusual date time again on Wednesday at 10. Okay.